conference without good attendees. So make this a wonderful conference. I'd like to thank our sponsors as well and the event coordinators who made all this possible. This is all fantastic.
特别想今天其实谢谢今天大家来。我觉得我这是第4年来Velocity China， 然后之前也是有就是 as foreign speaker， 然后不好意思中文讲的不是很好，我就大概尽力一下。那还有其实想特别感谢一下我们的赞助商今天其实我在学蛮久的怎么讲这些名字讲的念得比较正确一点。So first of all， 金赞助商有阿里巴巴集团，还有战略赞助商有Matrix， 网易蜂巢，主动线赞助商有日志毅，影响力赞助商有云智慧Broadview， 中国电力出版社、人民邮电出版社、华章科技，还有图灵教育，谢谢大家。然后今天谢谢今天其实也特别感谢，就是说我们今年是在一个新的地方比较地方也场地蛮大的然后也有一些就是我们program committee 还有 already staff， 我们也在想说今年 industry 有什么是比较热门的话题，比较就是请一些特别的 speaker 过来讲一下，分享一下他们的经验，然后让我们回去这个工作的时候可以比较多一些 data， 就知道大家 industry 在做什么这样子。就是说希望大家今天你们有什么 feedback 的话可以跟我们讲，也可以跟Douglas 他们讲就是 already staff， 然后希望大家enjoy the conference and yeah, so here I think the first speaker is you.
It is.
So actually you are the first speaker. I'm going to introduce you real quick. So for those people who's probably most of you are very familiar with you already. So he's deep in the space of ops and DevOps, and he runs his own conference in the US as well. So it's been his 4th year in Velocity China, and looking forward to his talk. All yours.
Thank you. So one of the things that I try to think about when Velocity comes around every year is that Velocity is about large-scale web systems that perform well. But that's a very simple idea. There are a lot of moving parts to high-performance systems. In general, no one wants to run a large website off of a high-performance phone or a high-performance server. They want to run it in a high-performance data center with lots of systems. So there are many systems that coordinate. There are many users. So in most large-scale web services, when you think about the computers that power that service, there are millions of computers because you send JavaScript down to a browser and that code executes on customer computers as well. So you're dealing with very large-scale distributed systems. And the problems when systems are distributed become much more complicated to reason about and to solve. So I have a very dense first presentation that's going to require everyone to think very hard. So I'm sorry, you have to think very hard in this. But I would like to ask first, I present a lot in the United States, and there are a lot of people in the United States that don't have a strong math background. But I understand that math literacy is very good in Beijing and in most of China. So how many people here know some statistics? Averages, standard deviation, things like that? Okay. So there's going to be a little bit of math in this talk, but what I want to get at is the idea of how to measure services to make sure that they're performing well for users, and how we quantify that. And I think that we do it wrong in the industry. So first, what is quality of service? So quality of service comes down to three basic components. So one is availability. The service has to actually be accessible. The user has to be able to get to the service to get the data back. That's usually very easy to measure. It's either up or it's down. The users are coming or they're not. The second one is correctness. So you can't have good quality of service if you're in a telephone system. The quality of service is very bad when you dial a number and get the wrong person, right? So it has to work to its function. So the system has to perform the expected operation and give the expected result back. And the first two things are usually not considered so much in quality of service because people assume that they are already the case. You assume the system is available. You assume the system is correct. So people focus, and I will focus on performance. So this is really about satisfying a user's productivity goals. So when I use a telephone, when I use my cell phone, I expect to dial a number. I expect it to ring. I expect to be able to have a conversation that's clear and low latency. Otherwise, I can't talk. I can't talk to my children at home. I can't talk to a business partner. So I need those things. And web services are the same way. When I search for products online, I need to type in my search. I need to get results. I need to be able to put it in a cart. I need to be able to purchase that. And I need to be able to do that. And it should not take me hours. It should take me seconds to do that. So how do you measure that? So some basic things that people mistake in measurement is that they use incorrect units. So the first thing is that 7 is not a measurement in any real engineering system. You have to have units. It has to be 7 something. Is it 7 people? Is it 7 computers? Is it 7 seconds? And when you're measuring time, you should always use seconds to measure time. You can use microseconds and nanoseconds, because those are SI versions of seconds, but not hours. Not days, not years, and absolutely not months. Months have the inconsistent number of days in them. So it makes sense sometimes if you have very low measurements. So say I'm looking at new customers coming to a website. I want to measure that in seconds. It might be 0.00013 customers per second. That's a hard number to think about, but you should still measure it in seconds. And then annotate that in 4 customers per day, 12 customers per day. But measure it in seconds. And there are 2 ways to measure systems. And this should be very obvious to anyone who has ever built a web system. Is the first one and most common one is synthetic measurement. This is when you use the website and you measure how long it takes. So this is typically done by developers and engineers. And then they codify that. They take that exercise and they put it into a monitoring system. So the monitoring system will, every minute or every 5 minutes, connect, do a request, measure the response time, the latency, the correctness, the availability, and record that. And that is incredibly useful for correctness and availability, but it is not useful for performance. Because the one customer that does not matter to your business is the monitoring system. No one cares if your monitoring system can place an order or do a search. You care if your customers can do that. So the second type of monitoring that we use is called passive monitoring. So this is observed monitoring. We want to actually watch people using the system. So you can do this through web logs, you can do this through JavaScript, you can do this through all sorts of mechanisms where you observe actual users using the system. It's the user's browsers hitting the system, measuring latency. It's web applications asking a database for an answer and measuring the latency. Internal service APIs, when you call microservice APIs, measuring latency of every request. So this passive measurement of real work gives you an idea of the actual performance and availability of the system as well. So The problem with doing synthetic measurements is that they don't represent real users. The passive measurements also have challenges as well. So one problem there is that synthetic measurements always happen every minute from a monitoring system, right? Every minute or every 5 minutes, very, very periodic. If you have lots of users and they're all asleep, they're not using the system. So you have a very variable rate of arrival. And so the only thing that you could guess is that people will actually arrive with a Poisson distribution arrival rate. That's the only thing you can say. So understanding how this data works is really interesting because it requires more math. It requires more statistics reasoning about what's going on. Because when you look at lunchtime, and you look at dinner time, and you look at breakfast time on your website, you're looking at different sets of data, very different. Some have many, many samples, some have very few. So the question becomes, if I have 10,000 customers that come over 1 minute to my website, what do you look at? What performance do you really look at there? Do you look at the average? Do you look at the median, the variance, minimum, maximum, 99th percentile? So it's very common to look at 99th percentile. But I have to ask why we're doing this. So I want to think about quality of service. People, engineers, think of quality of service as systems. But remember, there are users on the other end of the system. So let's use a metaphor. Hospital. You have 500 patients in a hospital, and you take all of their temperatures. Do you tell the doctor the average temperature of the people? It's horrible, right? You could have people dying. So the average temperature is not useful. The minimum temperature is not useful. The maximum temperature might be interesting, but not very useful. The interesting part there is that you actually have thresholds of danger, right? You have Celsius or Fahrenheit conversion. So you have 30 body temperature, and then say 3 degrees higher than that is dangerous, and 5 degrees higher than that is very dangerous. Right? You can die. So when you look at something like a 99th percentile, and you try to figure out what that means for people and their health, it doesn't make much sense anymore. So, why do we measure these things in the first place? So we measure these things so that we can improve the system. We want to measure them to make sure that we're delivering the quality of service that we expect, and that we can detect changes in the system. So you can see that. The changes that happen in the system that you're looking at. So in our case, are users happy? Are they healthy? So whether or not users are happy and the system is fast enough to serve them is really what QoS is about. So this is actually what a latency distribution of an API service looks like in our system. So this is over a 5-minute period. This is 2.2 million samples. So we do 2.2 million requests over 5 minutes. And this is the distribution of their latencies. Right? So maybe a little hard to read, hard to think about. But we can put some things there. So this green line is the average. This is the average latency in the system. So if I gave you one number that was the average, that's around 415 microseconds. That doesn't tell you what this curve looks like, this distribution. So this is a median, 25th percentile, 75th percentile. The 99th percentile is over 1 millisecond. The maximum is 47 milliseconds outside this room. So it's this is a much more descriptive representation of performance. It also shows us very interesting things in that we have different modes. Right? So if you think of people, you probably have 3 modes in a hospital. You have normal, you have sick, and you have very, very ill. In our system, we have things that hit cache, and different various workloads. So this represents 5 different workloads that are in our system. So what is a 99th percentile? Very quickly, a 99th percentile is in our case a latency where 99% of the samples are less than that latency and 1% are higher than that latency. Very simple. Math is a little hard to explain. But we use quantizing in general to describe behavior. So most quality of service guarantees are given in things that look like this last statement. For our API requests, we expect the 99th percentile to be less than 1 millisecond. So I want to write some questions about that. So for our API latencies, well, we have a lot of those, and they happen at different rates over time. So if I look at lunchtime, it's very busy. If I look at breakfast time, it's not very busy. I'm applying a 99th percentile over a different number of samples. Does that make sense? Why is it 99th percentile? Why is it not 95th or 99.9 or something else? Why is it 1 millisecond? The 1 millisecond is actually probably the best reasoned thing in this slide. Right? So as a systems person, I could say that I want to deliver my service faster than 1 millisecond. Or if it's a website, 300 milliseconds. If it's a database or a disk, maybe it's 100 microseconds. But I can understand what's reasonable to deliver, so I can set that. So I think that we can do a lot better than this. So the problem with percentiles is that when you look at in a hospital, if I say the 99th percentile of body temperature should be healthy, if I get an alarm that says, uh-oh, 99% of body temperature is too hot, that tells me that 1% of the population at least is too hot. Doesn't tell me how hot they are. That's a big problem. It doesn't tell me how many people in the population. So instead, we can do something, an inverse quantile. So instead of saying, what is the 99th percentile, we can say, what is the percentile at 1 millisecond? And if I ask that of this sample set, I get 96. So it's 96 percentile. That tells me that there are 2.1 million samples faster than 1 millisecond and 88,000 slower. So by using this technique instead, by turning quality of service upside down, we can do some interesting things. This graph is a latency graph of a website. So it's a little different, not the API. So the purple line is the 99th percentile latency. And the red line is 1.5 seconds, 1,500 milliseconds. And we see 3 points in the graph where it goes too high. So 3 points that are bad. The black line is the number of users using the site. So everybody thinks about this. It was very bad at 5 a.m. in the morning. There were very few users on the site. It was not quite so bad, didn't violate our constraints, but there were very many users on the site. If we apply an inverse percentile on this for 1.5 seconds, we can actually see the percentage of users that received too slow service. So this is the percentage of users that had a bad time. Almost gets to 20%. But remember, 20% of users at 5 a.m. can be a lot less than 1% of users at peak time. So if we look at the number of users, green, times the purple, we get the actual users. These are actual individual users per second that are affected. So we affected a lot of users here. And if we integrate over this, we actually show you how many users are unhappy. And we look at our failure here at 5 a.m., we can see there's a big increase. The increase from here, from 7 p.m. to around midnight is the same. We hurt just as many users in the middle of the day as we did during our outage. But because of the way we're thinking about quality of service, all the engineers are all worried about the outage. But this happens every day. That only happens every once in a while. Outages, you don't have outages every night, once a month, once a year, especially for an hour, right? But this sort of service degradation happens all day long, every day. So you need to start thinking about individual user experience and the quantity of users that are affected by service problems. So instead of quantiles, you want to think about inverse quantiles and individual users. And that is, think about users.